Okay. Last time we finished up with the Wilcoxon signed rank test, and we started the Kruskal-Wallis test. But I still have a little more to do with Kruskal-Wallis test. That should probably take the rest of the hour today. And then Wednesday we'll start our last chapter of new stuff. And that is chapter 17. We're going to skip chapter 16. And so chapter 17 is quality control, quality statistics. Pretty interesting stuff. But, question?
What's chapter 16 about?
It's about it's something you computer science people would like, but it's about the bootstrap method and basically doing statistical inference via simulation. But it involves a lot of programming and stuff, so this takes too long for a class like this. But so, any questions about the signed rank test? Still remaining. You guys, did you find your Launchpad homework? I sent an email about it. It is. It actually says quiz on it, and I found, at least so far, that the questions in their quizzes are more accurate. So I'm not having the errors that we saw in the homework problems. And so if I make quizzes instead of homework, but I count them as homework, then I think it's going to work a little bit better. So the deadline on that is Wednesday. That's today, right? No, today's Monday. Yeah. That's a tough weekend. And so by Wednesday, by midnight, you have to have that quiz done. Now, it does not. It has one question over the Kruskal-Wallis test, which I'm going to finish today. But that question only covers stuff that I did last Friday. But I'm not going to go back and add questions from what is today. So what I said in my email is that to finish the Kruskal-Wallis test, it'll be like a technology kind of thing. Use SAS to do this, and that'll be next week. It'll be due next week. Okay? So, for today, I want to do an example from the Kruskal-Wallis test. Let's see. How do I get? Here we go. Yeah, like that. So, the Kruskal-Wallis test. I've had this on the board a few times, so this should be old hat. This is the non-parametric version of what? Of a one-way ANOVA table. And essentially, what it turns out after you do the ranking and all that within groups, it's basically a one-way ANOVA using ranks instead of the raw values. The p-value you get if you just replaced the data values in SAS with the ranks of those data values with ties and all that, you'd get a p-value that's very close to the one you get from the Kruskal-Wallis test. So this is the Wilcoxon rank sum with more than two groups. More than or equal. But if it's just two groups, we call it Wilcoxon. But more than two, Kruskal and Wallis extended it. And so it's done a little bit different. The Wilcoxon rank sum test with two groups, you get the ranks, and then you circle the ones that came from one of the groups, and you sum those. Here, since you got more than two groups, you get the sum of the ranks from all of the groups. You don't leave one off like that. Right? Turns out that you could, because you could figure out what the last one is if you know the rank sums from the first three. But so we'll get rank sums in each group. Now I need you to remind me where we got to last time in terms of formulas. I know I had given you the basic formulas of how that would be. Oh, I got some papers to get back today too. So
I had stuff with letters.
Letters. Yeah.
We x squared.
Chi-square.
Okay. So is just a coefficient across, and it's sort of the inverse of the variance. Remember the variance term before we derived had 12 on multiplying by the variance, right? And then it had a summation, and summation I equal 1 to capital I, so number of groups, and then Ri squared over Ni, and then, well, let me write it. This should all be in your notes. We had that, and then after class, somebody, I don't remember who, said, now wait a minute, this coefficient, is it distributed all the way through? And real quick I went, oh yeah, there's supposed to be brackets around that, but that's not the case. So as soon as I got out of class, I looked at my notes, oh wait, no, the brackets should be here. So that coefficient is only times the sum, and this is outside the sum. So you get this term, and then you subtract off 3 times 1 more than the total sample size. Okay? So put the brackets around that. Just the book doesn't have the brackets. It has what I have written here without the brackets, and I guess it's just assumed that since there's no subscript in there and no parentheses saying to include that in the sum, that it's not included in the sum. But to make it obvious, go ahead and put brackets in there. Okay, so then we said, and this is about where we quit, I think, last time, H is approximately chi-square. And do you remember what the degrees of freedom were? I minus 1. So 1 less than the number of groups. All right? Okay, so we're working with the assumption here that all I of the groups, the null hypothesis would say all I groups have the same distribution. Right? The alternative hypothesis, at least one of the distributions is different, but most of the time we go ahead and say that from the perspective that the difference is in the center of that distribution. So you tend to systematically get higher ranks in one group than the other groups. So at least, and this is in the textbook, at least one group has systematically, that's the word they used, systematically that's a word. Systematically higher values. It doesn't necessarily say the mean is higher or the median is higher. They just, when you rank them, you tend to get higher ranks in at least one of the groups. Right? So we'll treat that alternative hypothesis. Okay, so now take a look at an example. This example is in the book. What an agricultural experiment, and this is actual data. He's got a a footnote to this, to the paper that was published, but it's about weeds in the cornfield and what the yield is of corn, and so depending on how many weeds are in that field. So I've actually been involved in a few studies like this where the scientists will classify acreage in terms of how many weeds there are per square meter, right? So a square meter is basically a 3-foot square on the ground. How many weeds are growing in that? And on average across the field, how many are there? So 0 means your herbicide is working. You've got no weeds. You've got corn plants, nothing else, right? And then you only get 1 per meter, 1 weed per meter, 3 weeds per meter, or 9 weeds per meter. So they've classified this experiment into those 4 groups. So you get the setup. So then the corn yield is bushels per acre. That's the typical unit. So in this study, they used 4 different observations per weed group. So they got 16 total. So N, capital N, is 16. Then each of the little n's are the same for this problem. And they're all equal to 4. Okay? So now let's see how we compute those rank sums for each of the groups. Let's see.
Out of curiosity, wouldn't you have compounding errors on that? 'Cause
Wait.
I'm assuming they didn't count the whole field, but they just took random samples.
They don't give any more information about this particular trial. What did I do? I missed a slide. That one. They don't give any more information about how this trial was set up to know whether they actually controlled the weeds, right? So they went in and thinned them out to get none or 1 or 3 or 9, right? And they're probably fairly small plots, and so then maybe they could do that. Or if they just said, well, on average, we've got... So, yeah, if it's a big field and they're just estimating and then they're classifying, oh, this field had an average of 1 weed per square meter, then yeah, there's going to be more variability in that study, larger errors, so harder to find statistical difference, right? But they even do these agricultural experiments sometimes in greenhouses. You know, they'll have literally a square meter and they'll plant a tomato plant in that or something, right? And then to say, well, if it was out in the field, this is what the stress would have been on it. So anyway, we're not here to critique the study design, but those are things a statistician should think about. Okay, so just looking at the 4 observations for each of those groups, we have means of 170 for the 0 weeds, 162.8, so about 163, 161 for 3 weeds, and 157 for 9 weeds. Just doing the eyeball test, what do you think? Does the number of weeds have an effect on your yield?
Yes.
Yeah. So they go in what I call dose-response relationship, right? The highest yield is when there's no weeds, and the lowest yield is when there's 9 weeds, and they step down. It's not necessarily linear, but they step down. So eyeball test, yeah, it looks like there's some evidence here that weeds have an effect. Now, would you do regular ANOVA, which is normal based, right, on this, or would you think we should do the Kruskal-Wallis test, a non-parametric test? And what in those observations in any of the groups, right? And there were some that would probably be, I would say that, but look at the standard deviations. What do you notice?
Two groups are double the other.
This smallest one is 4.4. The biggest one is 10.5. So you're more than double. So remember, that's an assumption for ANOVA. So at least one assumption is not being met here. So it probably says, well, you should use the Kruskal-Wallis test. Okay, so we've already seen this slide. Let me go to the next one. What's been done here? We ignore group and we rank, right? So 16 observations. The smallest one in the entire data set was 142.4. The biggest one was 176.9, and we rank them. There were a few ties. Here, these two are tied, so they get 12.5, 12.5. So this is the 12th one, the 13th one. The average is 12.5, right? And it looks like there are there any other ties? Sometimes you get whole numbers when there's ties if there's 3 of them. Right? I don't see any other ties. Do you? Okay. So I had to make a slide that had the groups with the numbers in the same slide that I had the ranks, so that I could figure out which one's which. So what do we do here? Okay, so let's look at the circle all of those and then get the sum. So 166.7 is right there. 172.2 is right there. 165 is here. And 176.9. Sum those 4 ranks. So the sum of the ranks in the first group, and actually it'd be easier if I use the subscript of the number of weeds rather than 1, 2, 3, 4, but I would put R sub 0 if I was doing it, but I'm going to match the book and I'll leave it as a 1. So first group, right? So that sum is, what'd you say, 52? If I've learned anything, is don't trust Taylor doing math in his head.
No,
so.
normally the calculator is what I screw up on. So.
Okay. Now my 2 kind of got a tail on it, so it looks a little bit like a 3, but that's 52.5. Okay? So doing that same thing, I did this one in advance so it wouldn't take us so long, but the number of the group, so 9 weeds, 3 weeds, 1 weed, and then here's the 4 with zeros, right, which we already did. Here were their ranks, and we summed them, and indeed we got 52.5. So now do the rest. Group 1 got a rank of 4, and a rank of 6, and a rank of 11, and a rank of 12.5. Does everybody see what I'm doing? All right, so I went to all the ones that were marked as a 1. And what is that sum? 33.5. Okay. Then the third group, rank of 2, 3, 5,
15.
and clear up here at 15. There's your outlier in that group, right? So all the others were pretty small, and then that one shot way up. But and what'd you say it is?
25.
25 even? And the next one was also 25? Okay. Now, let me go ahead and write down the ranks of that 9 group. So I have a 9 up there. Which adds 25. Now, if the null were true, what would you expect to see for those rank sums?
Expect them all to be equal.
You expect them all to be equal. And what would they be equal to?
N times n plus 1 divided by
34.
What's the sum of the first 16 integers?
136.
Okay, and how'd you get that?
I took
So
the
that
rank sums from each group and had them run together.
that's cheating, but it's okay. The sum of the first 16 integers. Remember that we had that formula?
Yeah. N times n plus 1 over 2.
What'd you say?
N times n plus 1 over 2.
N times n plus 1 over 2. Do that number. 16 times 17 divided by 2. Which would be 8 times 17, which is what?
34.
34.
34.
Did in my head.
Okay?
That'll give you 136.
Yeah, it's like that.
I was going to say, that's not right. That's after you're doing
Yeah.
this.
So that should be 136.
Yeah. 136.
Yeah.
And then you divide by 4 again to get the
Right. So that the total available ranks is 136, right? And then you expect them to be equally distributed amongst the 4 groups. So then if you take 136 divide by 4, now you get your 34. So this is expected under the null. Right? So you got a 52.5, a 33.5. That one's about where you'd expect. But this one's way bigger than you would expect. These two are enough smaller than you would expect to offset this one that's way above. Right? So again, eyeball test says, yeah, it looks like there are some differences going on here. Right? The question still remains, though, is it statistically significant? Okay, well, let's keep going. I wanted to, before I show that, I want to compute the H statistic. Let's go back. I've got 12 over 16 times 17 as that thing out front, right? Now, read to me what the ranks were from the 4 groups. I can remember a 52.5,
33.5,
and then 33.5.
and then 2.5.
Okay. So that's a 25. It's an ugly 5. Okay? And then I need to divide each of those by their sample size. So rank sum squared divided by sample size. Sample size in each group is 4. Now I've got some bad notation here I just noticed. I've got my summation symbol, but then has been done by that. Right? So scratch that summation symbol. And then I still need to subtract off 3 times 16 plus 1. And I'll wait for the calculators to stop humming, and you tell me what that equals. I guess I'll squeeze it in down here at the bottom. Somebody got it?
I get like 5.56.
I get
5.5. Give me a decimal place. 4.3. Okay? So those that are doing it got that. Have you do the entire thing, because that'd take half the hour. But I might say, given that the ranks of the rank sums in each of the groups were these four numbers, compute the value of the test statistic H, or something like that. All right? Now, how do we decide if that's statistically significant? How do I get a p-value? Well, we know that that H is approximately distributed as chi-square with how many degrees of freedom?
Big I minus 1.
Big I minus 1. So that's 4 minus 1. That's not a 1. 4 minus 1 degrees of freedom, so chi-square 3. So I can use my calculator that has a xCDF function on it. So the p-value is equal to the chi-square CDF function on your calculator from whatever your H was, in this case 5.56, up to infinity, so a bunch of 9s, and then degrees of freedom.
Get 0.13484.
0.1348. Okay? So now make a conclusion.
Fail to reject the null.
Do not reject the null.
This is bigger than our alpha level, which I'm not sure we ever said. So when in doubt, you use 0.05. So this is bigger than 0.05. So we fail to reject. So that's not the conclusion. What is the conclusion?
There's not a statistically significant difference between the yield of the corn.
Okay?
Oh no,
So-
sorry.
Same
The
distribution.
distribution.
Evidence. Now, Brent, I'm going to jump on you. Brent said there is no evidence.
Statistical evidence.
Right, there's not statistically significant evidence. There's some evidence. Our eyeball test said, hey, it looks like there's some evidence here, but rule out just random chance. It's possible you could get those yields look kind of good just by random chance. Right? Sample size is pretty small, so you don't have a lot of power here. There's evidence conclude. Now, I heard you guys trying to get the verbiage just exactly right, that the distributions are different or whatever, and that's good. I want you to do that. But it's okay, at this stage, it's okay to say it more in English the way that the botanist or whoever you're working with would say it. What do you think about yields of corn related to the number of weeds that are growing in that corn? Not evidence to conclude that weeds affect corn yield. All right? Conclude that, and I'll say one thing more, the number of weeds. That the number of weeds affects corn yield. And that effect is through the shape of the distribution or the location or whatever, but it's just, it doesn't have an effect. Okay? Question?
So that's not too broad. You would say that weeds are between 1 to 9 per square meter affect corn yield. You would say weeds in general.
Yeah, to be more technically correct, you would say, well, I can't make any inference beyond where I have data. I have data from no weeds to 9 weeds per square meter. But I don't know what happens if you get 20 weeds, right? Maybe then you have an effect. But you're right. You have to kind of limit to where you actually have data. Okay? Now let's go back and see what the software does with this. So we got a test statistic of 5.56. And you guys confirmed that with your computations, but I did it in advance, so I got the same number. And now I'm rounding to 2 places. You gave me a couple more. And then using our calculators, we used the x squared CDF function, and we got that p-value. Then in the book, they show you the output from 3 different software packages. First one is Minitab, then they do SPSS, and then they do SAS. And I skipped the SPSS one because all it did was give a conclusion. It doesn't show any statistics or anything. It just says, there's not sufficient evidence, blah, blah, blah. But I don't know how well you can read this, but I wanted to show the Minitab one, even though we don't have Minitab, because it does one thing different than SAS, which I like. Down here, you'll notice there are 2 different 8 statistics. The 5.56, which matches what we got, and then a 5.57, which is just a hair bigger. And this one out here has in parentheses, adjusted for ties. Okay, so SAS and that line of the Minitab uses a slightly different formula to compute the test statistic than what we did, that adjusts for the change in the distribution when you have ties in there. So if there's ties, then it strays a little bit from the chi-square distribution, and there's an adjustment that's made that's beyond the scope of this course. So
Ties you have, is a difference?
the bigger the adjustment, yeah. The bigger the adjustment. Here there's hardly any. There's only one tie in the whole thing. So the difference between unadjusted for ties and adjusted for ties is only at the 2nd decimal place. But then it gives the p-value, and so for the one that we did that matches that one, p says 0.135, which is what this rounds to 3 places. Okay? So we got that. Let's go to the SAS output. This is copied out of the textbook, so it looks prettier than what you actually get if you run it in SAS Enterprise Guide. It's just formatted nicer. But this is I'll show the one out of Enterprise Guide next. But this is what SAS gives you. It gives you more information. But look at the chi-square, Kruskal-Wallis test, chi-square test statistic. 5.5725. That's adjusted for the ties. That matches the Minitab 5.57. So adjust ties.
So it automatically does that?
Yeah. Actually override it if you program, if you write the SAS code and don't rely on the menu-driven enterprise guide, you can get in there and there's an option you can give it to tell it to adjust for ties or not. The default is to do it. And I'm not ever not want to do it. It's more accurate this way. And the p-value real close to what we got even when we didn't adjust for ties. Right? Now look up here. Here's the sum of scores is what it calls those rank sums within each group. And those match what we got. 52.5, 33.5, 25, and 25. Then it has expected under the null. There's the 34 that we computed a while ago. So it's the total rank sum, ignoring groups, divided by 4. Divided by how many groups you got. Right? And coefficient that's sitting out in front, right? I said it's the inverse of the variance. So you can figure out where that number comes from. We don't really need it because even with our handheld calculator, we don't use that. We use these numbers and we can come up with the chi-square test statistic, right? Which kind of has all that built into it. And then what's this mean score? Average of the ranks in that group. So the rank sum was 52.5. If you take 52.5 divide by 4, you get 13.125. And this is to try to sort of make it similar to looking at means of yields within a group. The mean score within this, right? So if you did a rank transformation of the data and just computed means, that's what you'd get. And then let's see, I've got, that's that slide. Then this one, I ran the data myself then in SAS Enterprise Guide just to confirm that it's using all the same options and all that as what the book had. And like I said, it's not quite as pretty as the previous one, but it's exactly the same numbers. 52.5, 33.5, and so on. Everything's the same, including the p-value. Right? So we've already said all this, but just to reiterate, we look at the p-value, 0.1344. Since that p-value is greater than 0.05, we fail to reject the null. Two ways that you could say it. This is the way that I would normally teach students to always start with there is sufficient evidence or there is not sufficient evidence to conclude that the number of weeds affects yield. Right. I copied this out of the book. This is the way that he made his statement of conclusion. This small experiment suggests that more weeds decrease yield, but does not provide convincing evidence that weeds have an effect. Okay? So I like acknowledging that it looks like, there is something going on. It's just this study was too small. You've got a power problem, not a weed problem. Right? So there is an effect due to weeds. It's just with only 4 experimental units per group, you don't have enough power to pick it up.
So is that like when you do preliminary trials? Is that kind of how your conclusion would go?
Yeah, often if you have what we call pilot studies or phase 1 studies, then you're not always worried about whether you get statistical significance or not. You're more worried about, are you showing a trend? Does it look like, it looks like I need to control weeds because weeds do have an effect. Now, if I want to prove it, then I do a bigger study. Right? I bet you with even just 1 more per group, so you add a 5, 5, 5, and 5, if it's about the same, I'll bet that would have been enough to drop that p-value down to 0.05.
So what does SAS do to account for the ties?
You really want to know?
Yes.
That's a great question, actually. So I will show you how to figure that out for yourself rather than spending a lot of class time on it. If you go, I actually have not experimented with the help menu here, but if you go to this SAS on the web, SAS product documentation, it's under the help menu. It'll take you out to a browser.
It does that to me. You just said.
Is it known?
Oh, okay. Whew. Glad you guys have encountered that. I thought I was going to have to become an administrator. All right, so this is...
No, it'll happen again.
It'll happen one more time?
It happens every time I change.
Every time I want a different page? Okay. So here it says documentation, SAS procedures by name and product. Right, we're using SAS 9.4, so I'll click on that.
So it doesn't matter enterprise guide, though? I guess you have to go to the programming side.
Right. What SAS Enterprise Guide is, it sits above SAS, and it's a user interface. And it says, okay, here's some menus. Tell me what you want to do. I'll go tell SAS to run it. So it launches SAS in the background. So if you want to know what SAS is doing behind the scenes, you got to go to the documentation on SAS. All right. So let's see. How do I? Oh, I have to click here. SAS procedures. Now I don't know that I've even told you the name of the procedure here. SAS runs in the background. Actually, it was on the output. At the top, it says proc in par one way. Ooh, what does that mean? In par one way. Non-parametric, one way and over. Right? So that's the project. So you click on the first letter. It's in par one way, so click on that. And then in par one way, right there. And then if you ever want to learn to program in SAS, this is kind of how you start. You get in the documentation, and here's the default tab is syntax, so it shows you how you would type it in to run it on your own. But to answer questions like that, you go to details. And so, dang it. Yeah, tied values, contents of output, displayed output, statistical computations. Probably just one-way ANOVA tests. And then it'll break down by what method it's using.
Isn't that test statistics?
Yeah, see, I need to find, it says for Wilcoxon scores, which is what we're doing. It's Kruskal-Wallis test, but they're called Wilcoxon scores. The test is known as Kruskal-Wallis test. Exact one-way ANOVA has to do something different. I'm trying to just skim this and see where it talks about the adjustment for tied data. So this is hard to read if you've not encountered it before, but they're just trying to stay generic. So the score, T sub I, for the ith group, minus what would be expected. What do you suppose the sub-zero means? Expected under the null, right? So expected if the null is true of that score, squared, divided by sample size. Ooh, that was R sub I squared over Ni. And then, and that's why I said that thing out front was the inverse of the, and then down, C sub ij, and then times some function of the ranks. So they're saying that Ti has this form. And then they'll go on to tell you A bar is average rank. If you nothing here is telling me what that A function is. It's just the score. So the different methods. The Kruskal-Wallis method uses one way of getting that score. The others, and so I'm going to gamble and hit next page. And for blah, 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 blah. For Wilcoxon, it's just the rank. All right. Come on. There we go. Rank sum produces proc impar one way uses a continuity correction. It's never saying here that I see what the adjustment is for the top. They do talk about the adjustment continuity correction, which you can override, but the default is to do it. So, sorry, I thought I would be able to get into the answer, but that's probably. What's that?
The type scores.
Or like type values.
Or type values.
Yeah, but
we know where to find it now.
Yeah,
Somewhere in there.
there may not really be anything done. I'm probably not finding it because we're just using the ranks, but the ranks have the ties thing built into it. But the adjustment actually comes in the way they compute the distribution, or compute the p-value, is it's not quite chi-square if you have ties in there. So somewhere they may talk about that, but I clicked on the one about scores, and it's not in that part. But so your assignment, since you asked this question, okay? All right. I owe you a few minutes, so I'm going to let you go 4 minutes early today. Because 4 minutes isn't enough to really get started into chapter 17. But go ahead and start reading that chapter. It's about quality control in industry. So it's something that I've never dealt with in practice because that's not my area of expertise. But it is. I doubt that you'll ever hit quality control type statistics in any other class you have as an undergrad. So I think it's good this book has it in it.
Except productions and operations management.
Really?
Yeah.
Okay. So we'll see you next time.